Hello everyone. We are going to be looking at statistical inference. So, statistical inference is about drawing conclusions from a population. This is a population perhaps. And so here, if we take a sample from a population and then form conclusions about that sample, we relate it back to the population and we can say the same things about that population. Okay, so we're going to be looking at a number of key ideas in relation to that, on looking at the difference between population parameter and a sample statistic, and then we're going to be, at the end, we're going to be looking at how we can form confidence intervals. So here's the difference between our population and our sample. We want to know something about the population. So in our population, there might be many numbers of people in the population, okay, or number of measurements within a population. And the properties about the population we call the parameters, such as the mean amount or standard deviation. They are the parameters of the population. So then from that we can take a random selection of people, a smaller amount, and we call this the sample. Okay, and sample, the properties of a sample are statistics. We've got the mean and the standard deviation of our sample. Okay, so this is what we have to work with. And we're going to analyze these statistics and form conclusions based on the statistics, and then we can say hopefully we could say similar things about the population. Alright, so let's look at ways in which we can form samples. We've got random sampling. Every member of the population has the same probability of being selected. Okay. So that's the usual way of doing it, and random sampling can be done in a way that doesn't favor a particular outcome. All possibilities have to be equally likely. So a CAS calculator can produce a set of random numbers. For instance, we need a random number generator. That's the best way of getting a random sample. Then there's systematic sampling. So this is where a rule or some kind of procedure is used to select members to be in the sample from the population. So in this case, the rule might be every kth member of the population is sampled, and that assumes, though, that the time that the sample has been taken is representative of the population. Now that's not always the case. The time at which sampling can occur can actually favor a particular niche of the population which is not truly representative. So an example is a doctor is undertaking a study about sleeping habits, okay, and she decides to ask every 10th patient about their sleeping habits. Alright, what type of sampling is this? Well, if there's some rule or procedure to sampling, in that case, it's systematic sampling. Okay. Now, is it valid form of sampling? Well, it's not too bad. However, not every sampled member will be equally likely as it is in random sampling. Okay? Because what happens if the doctor is only working during the morning hours of the hospital? So she's only observing patients, every 10th patient that come see her during the morning hours, and exploring their sleeping habits. What about those night owls that come in the graveyard shift and their sleeping habits? That might be important as well, and they are more representative of the population as well, looking at all times of the period of sampling. So there are limitations to systematic sampling. You've got stratified random sampling. This is where we look for specific subgroups of the population, and from those subgroups of the population we do want to have them represented in our sample. So we want them in a similar proportion. So that word there is very important, a similar proportion. Okay? So let's look at this example. We've got a school that has 523 boys, 621 girls. Now you have to think, well, what's the total of the students there? So the total students at this school is the addition of the two. So let's work at that. So total students, add them two together, and we've got 1,144. All right. Now, if we're interested in finding out about their attitudes to sport and believe that boys and girls may respond differently, which is possible, then we want to have that same proportion of male and of boys and girls in our sample. And we want our sample to be 75 students. So there's 75 students in the sample. So let's determine how many boys they're going to be and how many girls they should be in our selected sample. So we've got to work out what is the proportion. Now a proportion is like a fraction. So what is the proportion of boys? So we take the amount and divide it by the total. Okay? Now that gives you a fraction, and we can represent that also as a percentage. So in that respect, we can use our CAS to help us do that. All right. So we had 523 out of 144. 1,144, there we go, times 100. All right, about 45.7%. Okay, and the same for girls. So girls, in fact, would be, the proportion of girls should be what's left, up to 100%. So we'll just approximate that. 621 out of the total. Okay. 54.3%. Okay, now, they're the proportions of boys and girls. So we need that same proportion in our sample of 75. So we now, for our sample, for our boys in the sample, we need 45.7% of percentage of our 75 students in our sample. Okay, and we can do that similar for the girls as well. So divide 100 times 75. 34, roughly 34 students. So this is a sample of boys. It's about 34 students of boys. And for girls, well, it has to be what's left, up to our 75. So we're going to have, subtract that from 75. And how much would that be? It will be also a little bit more. So little calculation, there we go, 75, take that amount, and 40.1 or 40.7, so it's about 41. Okay, so that looks at how we have to get the same proportion of boys and girls that are in the population and have them represented in the sample as well. And that's called stratified random sampling. Okay, now we also have the idea of a self-selected sample. So a self-selected sample is where the participants of the same sample, or of the sample, choose to participate in the survey. Now, the problem with that, it's very rarely representative of the population. Okay, because if there's a situation such as a morning television show conducts a viewer phone-in poll and announces that 95% of listeners believe that Australia should become a republic. Okay, well, what about those that are actually just listening at the time? So that's not fully representative of the population. And maybe a whole bunch of Republicans might be only interested in voicing their opinions. Maybe the monarchists are too disgusted and they can't be bothered ringing in and discussing such a poll on the radio. Or maybe the other way around. So, no, it's not very valid. Does not represent the population, okay? Because it's not random in the selecting of the participants. And the random sampling is what we're after to make it a valid survey. Okay, so considering those different types of sampling methods, what we're going to look at now is what do we do with a sample? Okay, so from our population, we're going to explore now from the sample, what do we get? Now, if the amount of people in a particular population are the ones we're interested in knowing about, then we can express the information as a proportion of the total. So a proportion is the number of observed outcomes out of the total number. So in this case we might have 1, 2, 3, 4 out of our population. Whereas if we just capture a sample of the population, we might get roughly a similar proportion of 1 out of the total we have there, 1 out of the 6. So the population parameter that we have there is our population proportion. We're going to denote that as a P. While the sample statistic in this case is our sample proportion. We're going to denote that as a P hat. Okay, so we can tell the difference between our population proportion and our sample proportion. So when samples are randomly selected, each different sample could have a different sample proportion. So the next time I take a sample, I might get 2 out of a possible 6 in my sample. So let's consider this example on how we can come up with our sample proportion. Alright, so in a 99 gram bag of lollies there were 6 green lollies out of 15 that were counted. What is the sample proportion P hat? So what we're doing to calculate P hat, we're looking at what is observed, the number that is observed, out of the total. So it's 6 out of 15, okay? And such numbers can be approximated or expressed as a fraction or as a decimal, okay? So in this case, we got that value of 40%, 0.4. Now, the decimal is the useful number to be used in calculations. Okay, very easy. Alright, let's try this particular example. So, Hanger person is interested in seedlings that can grow to more than 5 centimeters tall in the month of her study period. So then she begins with 20 seedlings and finds that 6 of them are more than 5 centimeters tall after the month. What is the sample proportion? Well, we have to think about how many seedlings there are in the population. Many, many, many. So we can't take a census of all the seedlings, so we're interested in just the sample. And the sample that we're looking at is sample of 20 seedlings. And what was observed was 6 of them. So we have a 6 out of 20 is our sample proportion of seedlings that are more than 5 centimeters tall. And that's what we're after. And the fractions, we can simplify it, 3 out of 10, and be ready to convert it into a decimal. Okay, so once we can identify our sample proportion, we're then interested in thinking about how this sample proportion can change every time we take a sample. So imagine here's a population of pink balls mixed into blue balls. So we've got different color balls all together. We've got a population of 20. So the population parameter we have here is 5 out of possible 20, so it's a quarter. All right. So that's the information about the population. Now, let's take a random sample. Let's take a sample of 5 balls. There it is. There's a sample of 5, and the sample proportion is, as you can see, 2 red out of 5. Well, that's a little different. Let's take another random sample, and this time we got 1 out of 5. And the third sample, if we select a sample of 5 balls here, this time we've observed 0 out of 5, which is just 0. And we notice that the values of the sample proportion are going to vary. They in fact have a sample distribution. They have the values of your proportion has its own probability, okay, and it's distributed across all the possible values that we could get of our p hat. Okay, now to help us work out what that probability could be and what the probability distribution of our sample proportion can be, we're going to explore the number of combinations. And we're going to use this counting theory, this number theory application, to help us produce our probability table for our sample proportion. So the number of combinations is if we've got the different possible samples drawn from a population. Okay, if we've got a population of, say, n amount, then the amount of combinations that of groups of size x out of n is given by this rule. So in this case, 5 things in total. How many different ways can we select 3 out of 5? All right, so let's do an example of how we can apply our combinations rule. So it's 5 factorial divided by 3 factorial, and then 5 minus 3 factorial. So we can see 5 factorial is 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. That's the whole idea of a factorial. And 5 take 3 gives you a 2, and then we need to think about what's 2 factorial. 2 times 1. Now, by expanding out all the products, we can see some common factors that we can cancel out. 3 factors of 3, and so on. So from that, we've got 20. What's left in the numerator? Divided by 2, which is going to give you a 10. Okay? So there's 10 ways we can get groups of 3 things out of 5 possibles. Now on the CAS we'll be using this function, NCR, okay, to get our number of combinations. Alright, so let's think about now number of different ways, different possible samples of drawing a population is the combination of the sample size n out of a population size, capital N. Alright, so draw a sample size of 6 out of a population of 25. How many different samples can we get? So the population number N, capital N comes at the top, and the sample size comes at the bottom. So here we go, on the CAS, if we did that, NCR of 25,6, we will get this. There's a lot. So there's many different possible ways you can form samples from a population, especially if the population size is really large. Huge amount of combinations. But we're going to use that to help us identify, well, what's the relative frequencies of getting a sample of a particular sample proportion out of the population. Okay. Now, let's consider this as a little problem. Now, if we have 5 apples, and then there's 2 and 4 oranges in a fruit basket, and 3 fruits are chosen at random, what is the probability of selecting 2 apples? Okay, so our population of fruit is made up of not just one particular type of thing. We've got 2 types of fruit. So we might be interested in, well, what's the proportion of apples in our fruit basket, and what's the number of combinations, or what's the probability, what's the number of combinations of samples we could get by selecting 3 fruit from a fruit basket with a total number of fruit in it. So what is our total number of fruit? So the total number of fruit is the 5 apples and the 4 oranges, so you get 9 fruit. Okay? Now, what we have is selecting a sample of 3 fruit. This is our small n. Okay? And we've got a population in our fruit basket, capital N, of 9. Then how many different type of samples can we come up with? Well, this is where we can draw on this idea of drawing sample sizes. So the total number of samples, different combinations of samples we could get, well, we can have from 9, we want to draw out 3. Okay? And then, let's say we're interested in selecting 2 apples from that. Okay. Well, from the 2 apples, we've actually got 5 different apples to choose from. But for a sample size of 3, it means every time we draw 2 apples, we're also going to get 1 orange. But there are 4 different oranges we can choose from. So we're going to have a mix of combinations occurring here. So the way we're going to approach this is thinking of the probability of selecting 2 apples. Let's identify this as x is our random variable here. We want probability of 2 apples. Well, let's consider all the combinations this is going to occur. Let's try this down here. Okay. Alright. So here we go. We have a total number of samples altogether. Well, the total number is what we're going to be dividing by in our proportion. This is like our sample space. So we've got a combination of 9 and 3. Okay, 3 into 9. So then let's consider the combination of 2 other combinations here. So first off, we're interested in getting these 2 apples. So we've got 5 possible apples to choose from, and we want to pick 2 of the apples. So this combination looks at the number of ways we could select 2 apples from a possible 5. This one identifies the apples. Well, every time we now select 2 apples, we also have to get 1 orange to get our 3 fruit all together. So the second combination is looking at all the combinations for oranges. So we've got 4 oranges, that's our total number, and we're going to be selecting 1 orange every time we get 3 fruit. And this is for our oranges. Okay, so what's important here is to notice that both of these numbers there, that adds up to a 3, okay, which is the sample, whereas the top numbers here add up to the 9, which is the population. Okay, so let's have a go at evaluating that. So using your NCR, we have, there it is. All right. Now we have 5 apples, and we're going to get 2 of the apples. You now pick. Now we've got 4 oranges, and we're interested in, we'll always get 1. And then we have to divide by our total. So we're interested in having, we've got a total of 9 fruit altogether, and we're selecting 3 out of them. And this is going to give us our probability. It's about 47 or 48%. There it is.